When people think about basic chemistry, they tend to think about people who are doing experiments with test tubes, doing titrations, dissolving solutions, and things like that. But the reality of when it comes to health sciences is that basic chemistry is going to represent much, much more. Hi, everybody. It's Dr. Snyder here at IRSC with your Chapter 2 discussion on Anatomy and Physiology I. Let's get right into it here. So when it comes to learning about basic chemistry for health sciences, the important thing to note is that it's going to create the basis for your understanding for virtually how everything in health science works. Because not only do we need to know basic chemistry to learn about the human body and learn about how all of the different parts of the human body will interact, it's also going to be a really big factor in how you can understand the ways that various types of patient treatments will work, because it's not just as simple as putting a patient in the hospital and putting a saline IV in their arm and then just go ahead and set it and forget it. There are various different types of medicines that we will actually administer to our patients through an IV drip, and it's going to involve a very, very close and very, very in-depth knowledge to what it is in that bag or what it is you're putting into that person's intravenous drip here. So when we need to know basic chemistry, one of the main things that we're going to be talking about when it comes to basic chemistry for health sciences is that we're going to be looking at these four main elements that make up the human body here. We are primarily, of course, made up of oxygen, lots and lots of water here, because oxygen and hydrogen are going to be our basic molecule for water. We know each water molecule is going to have two hydrogen atoms and one oxygen atom. The other thing to note is that we're going to be spending a lot of time talking about structures that are made up of carbon, because carbon is going to be found in all organic compounds. So when we're talking about carbon-based chemistry, this is how we are talking about things like organic chemistry. If you've ever heard people talking about, oh man, organic chemistry is so difficult to learn, it's mainly to do with learning about how carbon interacts with all of the different molecules of the human body. The last principal element that makes up the human body is going to be our nitrogen element. So nitrogen is going to be a big building block in all of our various proteins, nucleic acids, and then other organic compounds where you will also find carbon. Some other key elements to keep in mind here as we go through our basic chemistry studies are going to be calcium, phosphorus, potassium, and sodium. These first three, calcium, phosphorus, and potassium, are going to be very crucial for when it comes to the overall maintenance and development of our skeletal system. So our skeletal system is going to be made up quite a lot of calcium, as we can see right here, but there will also be a fair amount of phosphorus as well as potassium, and even as well as things like magnesium. Magnesium is also going to be found in smaller concentrations in our skeletal system, so it's going to be very crucial for the maintenance of very strong and healthy bones. Some other key things to keep in mind are going to be sodium. Sodium and potassium are going to be very, very important, especially when it comes to our learning of the muscular system and the nervous system as well, because these two ions are going to be very, very important, and as well as calcium, when it comes to the generation of action potentials as well as the creation of muscular contraction. So other reasons for why we want to keep in mind our basic chemistry for learning about health sciences is because the whole idea behind using natural methods for healing, or things that we call functional medicine, has really been exploding in the last couple of years here. So for many, many years, the traditional healthcare model was based around using the different types of diagnostic procedures that we have to determine a diagnosis, and then use that diagnosis to determine the appropriate medicine that we apply to that patient. But as society has become a little bit less involved with the use of prescription medication and more in tune with the idea of using natural methods such as dietary changes, lifestyle modifications, and even natural supplementation for the treatment and prevention of disease, these are going to be extremely important to learn about so that you can be well equipped to help have that discussion with your patients should they come to you and say, hey, I hear that magnesium is a hot button topic. What do you know about magnesium? And you're going to tell them that you know about magnesium because you learned about different things like magnesium chelates. So chelates are going to be a type of process that we use to bind our different types of supplements like magnesium to an amino acid. This binding process, this chelation process, is going to be what allows the magnesium supplement to be bioavailable or easily absorbed by our patients' bodies. This is very, very key because a non-chelated magnesium supplement, something like magnesium oxide, is going to have a very, very poor effectiveness. And that oftentimes, magnesium oxide tends to be kind of the poster child for when people talk about supplements that don't work. They go, well, you see this study about magnesium oxide and it doesn't work. Well, it's because magnesium oxide is a poor quality supplement. But some of our high quality supplements, like our chelated magnesiums, so things like magnesium citrate, magnesium glycinate, you can even have magnesium L-threonate and a couple of other different types of magnesium. Those are going to be readily absorbed by the body and as a result, much, much more effective in helping our patients achieve better health. So it's very, very important that you make sure to break open your textbook and read through this chapter because this is going to be huge, not just in this class, but for the rest of your career. You will never not go a point in your health science career and not think about basic chemistry. Let's talk about the structure of an atom next before we get too in-depth about each of the individual elements here. So first of all, let's talk about the basic structure of our atom that we see right over here. We have a central nucleus, which is going to be composed of our positively charged protons, our neutrally charged neutrons, and then this nucleus is going to have what's called an electron shell orbiting out here. The electron shell is going to be made up of our negatively charged ions called electrons out here. These electron shells are going to exist in a couple of different levels surrounding the nucleus. So when we talk about the different levels surrounding the nucleus, we need to talk about how we have an innermost shell that can carry a maximum number of 2 electrons that we see right here. This innermost shell is going to be in this situation, in this specific atom that we see right here, this shell, which is going to be the outermost that we see on this picture. This is going to be called the valence shell. However, if this individual element has more than 2 electrons in it, it is going to have an inner shell that's going to carry a maximum number of 2 electrons, and then it's going to have a secondary shell that's going to orbit right around here. This secondary shell can hold a maximum number of 8 electrons. And when we have this secondary shell is going to be considered the valence shell. More information about the valence shell can be found on page 54 of your textbook. When we talk about some of the individual numbers that you would find that describe each element on a periodic table, the first number to note is going to be the atomic number that we see right here. The atomic number is going to denote the number of protons that we find in an element. So we can see right here with our example of helium, we are looking at our atomic number of 2 because we have 2 protons out here. So that's why we use the number 2 to describe helium on the periodic table. Now, when it comes to the mass number, though, the mass number is going to be our number, which is the sum of protons and neutrons. So with our helium atom that we see out here, we're going to see that we have a mass number of 4 because we have 2 neutrons and 2 protons. When we move over to the atomic mass, though, the atomic mass is going to be slightly different because the atomic mass is going to include the total mass of protons, the total mass of neutrons, and the total mass of electrons. So this atomic mass number is usually going to have a decimal number to it, a lot of smaller numbers after, because the mass of an electron is very, very small, much, much smaller than the mass of a proton or a neutron. So that's why we're going to see an atomic mass number have that decimal point. When it comes to the atomic weight, though, this is going to be the number that we have found to be the average among the atomic masses of all the isotopes of a certain element. So what we mean by the term isotope is that we are talking about a variance of an element where we have different numbers of neutrons associated with that nucleus. So in our example that we see right here, we have a hydrogen atom denoted by our mass number of 1 because we have 1 proton and 1 electron that we see right out here. This is why hydrogen is going to be pretty ubiquitous when we talk about chemical reactions, especially throughout the body, because hydrogen is going to end up taking the place of when we're talking about the donating and accepting or the sharing of a single electron ion. So this is going to be our basic normal structure of a hydrogen atom. But when we get to a hydrogen atom that carries the 1 proton and 1 electron, but an extra neutron associated with that nucleus, this is still going to end up being a hydrogen ion because we have that basic 1 proton, 1 electron. But because it has the extra neutron, we're going to call this hydrogen 2 deuterium. Moving on to our next isotope of hydrogen that we see out here, it still carries that basic structure of 1 proton and 1 electron, but because it has an extra 2 neutrons associated with that nucleus, we're going to call this hydrogen 3 tritium. When it comes to the ways that different atoms can come together to make molecules, we need to talk about chemical bonds. For the purpose of healthcare science, there's a couple of different chemical bonds that we need to cover. The first of which is going to be our ionic bonds. Ionic bonds are going to be made when an electron is transferred between one anion and one cation. This is crucial. The sharing has to be between an anion and a cation because an anion is going to be an element that has an extra electron, which gives it a negative charge. This is going to be the atom that's going to transfer the electron to the cation, which is going to be the element that has a positive charge because it has fewer electrons than it does protons. This is going to be that crucial aspect. We can't have 2 anions paired with each other because they both have extra electrons. It has to be between a negatively charged element, the anion, and a positively charged element, the cation. So we're thinking about stuff like the combination of a positively charged sodium ion and the negatively charged chloride ion as well. This is going to give us our NaCl, known as a table salt. When it comes to ionic bonds, these are going to be bonds that are going to be relatively easy to break. This is going to be an example of why salts are so easy to dissolve when we put it into a solution, such as when we add table salt to water, it tends to dissolve very quickly and just make salt water. The next type of chemical bonds that we need to cover is going to be our covalent bonds. So covalent bonds are going to be more common when we're talking about healthcare sciences because this is going to be the type of bond where electrons are shared between 2 atoms. So this is going to be where we form our more stable types of molecules as opposed to something like an easily dissolvable compound. The reason why atoms are going to end up forming these different types of chemical bonds is because various types of atoms are going to carry various levels of reactivity to them. Because atoms need to follow what is called the octet rule. The octet rule says that having 8 electrons in the valence shell, the outermost ring, is going to be what makes an ion or any type of element stable. This is going to not apply to hydrogen because we end up just having the one electron in that valence shell. But for virtually every other type of element out there, we need to have 8 electrons in that valence shell in order to have a truly stable element. This is going to be where we see things like noble gases. So remember we talked about how each shell or each ring of electrons can carry a maximum number of electrons. So when we see the first noble gas here, helium, we see that instead of following the normal octet rule of having 8 electrons in its outermost shell, we see that helium is going to have a maximum of 2 electrons in its outermost shell because that's going to be the atomic number that we see right here. It only has the 2, but because that valence shell, that ring that we see right here, this first one can carry only a maximum of 2 electrons. So this is going to be a very stable outermost shell for helium. That's why we call them noble gases, though, because noble gases is going to be the collection of gases that are going to follow this octet rule, and they're all going to have that nice, stable outermost ring, that outermost valence shell full of electrons. We see that very well here with neon. As we see, neon has an atomic number of 10, so we're going to have 10 protons and 10 electrons in a neon ion. So we have this innermost shell, which is going to carry the first 2 electrons here. And then going back to that octet rule, we have 8 more electrons being carried in that valence shell. This is going to make neon very, very stable. This is going to be in contrast to different types of elements like hydrogen and lithium that do not follow the octet rule. They don't have 8 electrons in their valence shell. And in the case of hydrogen, because the first shell can only carry a maximum of 2 electrons, since we have less than 2 electrons in the hydrogen shell, this is going to make hydrogen very reactive. So hydrogen and lithium, because they have less than optimal numbers of electrons in their valence shell, they're going to be very, very reactive and very, very susceptible to chemical bonding. We see this octet rule play out classically with the formation of an ionic bond between the sodium atom here and a chlorine atom here as well. So we see that the sodium atom is going to carry 3 shells of electrons. Its valence shell is going to have just the 1 electron available, which is why it's going to be very reactive. It's going to be very open to sending this extra electron over to the chlorine atom that we see right here, which the chlorine atom, when we take a look at its tertiary electron shell, we see that there's only going to be 7 electrons in that outermost shell. So it really, really wants to have that 8th electron out here. So that's why sodium is going to be a natural partner for creating that ionic bond. It's going to donate that extra electron over to the chloride ion and give us our sodium chloride compound that we see right here. Conversely, when we take a look at the covalent bonds that we see right here, remember that when it comes to the covalent bond, we're talking about the sharing of electrons between 2 atoms to create that covalent bond. So we see right here when we're talking about hydrogen, and this is going to be actually how hydrogen naturally occurs in the environment. It's not going to simply float around as an H1 that we see right here. It's going to want to be more stable, and as a result, in order to be more stable, it's going to find another hydrogen atom, and then it's going to share the electrons between those 2 shells here to create what's called a single covalent bond. So the single covalent bond is when we have 1 pair of electrons being shared between the 2 atoms, versus when we go to an oxygen molecule that we see right here, O2, we can see that there's going to end up being 4 total electrons being shared. We have 1 pair of electrons being shared by the first oxygen molecule, or the first oxygen ion rather, and then 1 pair of electrons being shared by that second oxygen atom. So as a result, because we have 2 pairs of electrons being shared, we now have what's called a double covalent bond. And then in contrast to here, we can see how we have multiple covalent bonds being created in a single compound that we see right here. So we have a double covalent bond being shared between this oxygen ion and this carbon ion. And then we have another pairing, a double covalent bond here between this oxygen ion and this carbon ion, giving us our chemical compound of carbon dioxide, CO2. Even further than that, we end up having multiple types of covalent bonds. We have 2 types of covalent bonds to keep in mind here. They're going to be called polar and nonpolar. Nonpolar bonds are going to be compounds where the electrons are going to be shared equally between the atoms. This is where we think of like our oxygen compounds that is going to occur naturally in the environment, as well as things like carbon dioxide that we see here. So these nonpolar bonds, these nonpolar compounds, they are not going to carry a regional charge here. They're going to be a neutral charge compound, which is why they're going to be rather stable in the environment in this structure. This is in contrast to a polar covalent bond that we see right here. A polar covalent bond happens due to the unequal sharing of electrons between various ions in a compound. This is going to give us what we call a regional charge on that specific molecule. So we see this played out in our water molecules that we see right here. So we know that water is going to carry an H2O symbol. So we end up having 2 hydrogen atoms that we see right out here, and then our 1 oxygen atom that we see out here. Now, because our 2 hydrogen atoms and our 1 oxygen atom are naturally going to have an unequal distribution of the sharing of electrons, they are going to create this polarity to each of the water molecules. So we see that we have one side is going to be considered our positive pole. We're going to be the positively charged side of our water molecule. You can think of this as being 2 ends of a magnet. How we have one side of the magnet is going to carry a positive magnetic charge, and then the other side of the magnet is going to have a negatively charged end. So this is going to be our negative pole on the water molecule, giving us what we really kind of looks like our bipolar Mickey Mouse figure right here, right? Having this unique feature of polarity in a water molecule is going to be what allows water to have some unique properties to it. So this unequal distribution of electron sharing right here is going to be what allows our water molecules to actually stick together, because we're going to have one water molecule out here is going to have the positive pole pointing here and a negative pole pointing here. And then we're going to have another water molecule is going to come down here, and it's going to face in a repeating image. We're going to end up having that Mickey Mouse shape right here, where we have the positive pole is going to be in contact with the negative pole of the next water molecule right here. So this is going to be how we can create what are called hydrogen bonds. Hydrogen bonds are going to be very important to the human body because even though they have a relatively weak strength, it's this relatively weak strength of hydrogen bonds that make them so useful in the human body. Having low weakness means that they have a low energy requirement to create the new bonds, and they have a low or minimal, even sometimes no energy requirement needed to break that hydrogen bond as well. So that's going to be very, very crucial for the body. This slide shows us a better depiction of that chain of hydrogen bonds that we see going on throughout here. So we have This positively charged pole out here is going to be bound to that negatively charged pole of the adjacent water molecule that we see right here, and allows us to combine all of these into our hydrogen bonds. This is going to be crucial, especially for when we talk about DNA, because DNA is going to be held together by hydrogen bonds. All of those hydrogen bonds are going to be what gives water its main properties, especially when it comes to some of the most important properties that interact with the rest of the human body. So hydrogen bonds are going to give water, which you can find in your textbooks on page 69. It's going to give water the properties of cohesion and adhesion and surface tension. This is going to be a big reason why we end up seeing things like a meniscus that we see forming on the sides of our different types of things like a glass, or if we're using a test tube or things like that. If you remember in high school chemistry, you fill up a test tube and then you see that the test tube has this kind of an oval shape to the water here because the meniscus on the sides, as the water travels up the side of its container, the water is going to carry a high amount of cohesion, adhesion, and surface tension as a result of all of that hydrogen bonding. What is also going to be true of the properties of water is that it's going to have a very high heat capacity. This is going to be extremely crucial for us as people because having a high heat capacity is going to help us in a lot of ways since we are mostly made of water. Having a high heat capacity is going to be what enables us as people who are mostly made up of water to walk around, for instance, in a desert, very, very hot. Sometimes can get to be 120 degrees. Even in Florida here, the feels like temperature this summer reached around like 114 degrees. It was brutal. But otherwise, we have a very high heat capacity that we can withstand. It's a great reason that we don't just evaporate whenever we walk out into 114 degree feeling heat. It's also going to mean that water is going to have a less density to it when it's a frozen ice as opposed to when it is a liquid. That's a big reason for why whenever you put a bunch of ice into a cup, or if you take a bottle and then you freeze the water in it, the frozen water is going to appear to take up less space than the liquid water. As in On that same vein here, one of the key properties of water is that it's going to be a very universal solvent for the most part. It's going to be what helps us to do things like dissolve different types of compounds and create new types of suspensions and things as well. Water is also going to be extremely important as a lubricant, especially when it comes to the lubricant that we see between all of our various types of organs within the body, as well as our joints, which we'll talk about in our musculoskeletal units. But this lubricant is also going to be very crucial for the maintenance of or decrease of friction between all of our organs as they move together, because as we move around and change our positions, we do actually see our organs moving over each other. And of course, water is going to be extremely important to the chemical reactions in your body, especially when it comes to doing things like breaking down different types of compounds. Let's take a break here and check everybody's knowledge so far. So looking at the first question on our slide here, we're looking at asking, water molecules stick to one another as a result of hydrogen bonding. This feature is going to be known of as, we have answers A, cohesion, B, polarity, C, high specific heat, and D, adhesion. Take a moment to go ahead and think about your answer. You can go ahead and look it up in the textbook if you need. As we go through the answers here, let's take a look at some of the ones that we know that we can get rid of. So when we take a look at the answer of high specific heat, this is going to be a feature that allows water to resist evaporating too easily. So we can go ahead and strike that out because we're not talking about the ability of water molecules to stick to one another. When it comes to hydrogen bonding is created by the feature of polarity, but polarity is simply talking about the positive and negative poles created in a polar covalent bond. So this is not going to be unique to water molecules, so we can strike out polarity as well. When we take a look at the remaining two answers here, cohesion versus adhesion, this is going to be a bit of a test of your vocabulary as well, because when we look at the word adhesion, adhesion is going to reference when molecules can stick to one another of different substances. So such as when water molecules stick to the wall of their container, much as they do in a test tube or any other kind of glassware that we're going to use in a chemistry lab that might create a meniscus, versus cohesion. This is going to reference when water molecules of the same type are going to stick to one another. So the answer to this first question is going to be A, cohesion. Now looking at the second question here, asking the ability of water to resist shifts in temperature is due to its, and then we have our answers: A, carbon skeleton, B, cohesiveness, C, high specific heat, and D, lattice crystal formation. Just as we talked about in the first question here, having an ability to resist shifts in temperature is going to be more a consequence or more a benefit of water having a high specific heat, because we do not easily evaporate as a result. So people are made up mostly of water. So it's a very good thing that water has a very high evaporating point so that we can actually exist in very hot temperatures and hot climates without damage. Keeping up with our topic of water here for this chapter, we need to keep in mind that different types of electrolytes are going to interact with water differently, especially when it comes to different types of inorganic compounds versus organic compounds. So when it comes to inorganic compounds such as various types of salts, so we're thinking about sodium, potassium, as well as our typical type of salt, table salt, sodium chloride that we see right here. So these different types of electrolytes are going to have those ionic bonds, remember. And when those molecules that are going to have ionic bonds enter an aqueous solution here that we see, our just H2O water solution, what's going to happen is this sodium chloride crystal is going to go through a period of dissociation or ionization, meaning that each of the atoms in that molecule will have their ionic bonds broken apart because they're going to interact with the polar charged molecules that we see right here, all of these water molecules. And as they interact with all of those water molecules, each of those electrolyte atoms are going to have what's called a hydration sphere formed around them, which is the collection of all of those water molecules that bind to that single electrolyte atom. This is going to be typically the same when it comes to different sorts of organic compounds, as well as things like glucose that we see right here. When we have different types of organic compounds like glucose that enter a watery solution that we see right here, they are going to go through a series there's going to be a series of breakdowns occurring here as well, because the different types of polarity in the glucose molecule will also interact with the polar charged molecules of water that we see right here. So we're also going to see this hydration sphere form around that organic compound, that glucose molecule. When it comes to things like fats and oils, though, they are going to interact quite differently when they enter a watery solution, because whereas we have with our different types of molecules like sodium chloride and glucose, because they interact with the water around them, they are going to be what are called hydrophilic molecules. Hydrophilic molecules will readily dissolve in water. However, things like fats and oils, they are not going to readily dissolve in water. Therefore, they are going to be what are called hydrophobic molecules. This concept is very important to understand, especially when it comes to understanding our cellular biology, because our cells contain what is called a phospholipid bilayer. The lipid means it is made up of fats, which means this phospholipid bilayer, which makes up our cell membranes, is going to have a hydrophobic property to it, which is very good because it means that our cells are not going to dissolve in the water around them. That's very, very important. On the topic of various types of solutions, we need to next cover the concept of pH values because the regulation of our body fluid pH is going to be one of the more essential parts of maintaining our homeostasis, especially when it comes to regulating our blood pH. So pH is going to be a type of measure that we use to describe the number of free-floating hydrogen ions present in any type of solution that we're looking at, and it's going to be on a logarithmic scale, meaning that it's simply going to be a measure of a tenth to the power of whatever number we're looking at on the pH scale, which we'll look at a future slide here. The overall thing to keep in mind is that solutions that have a more acidic measure, they are so because they have a higher degree of free-floating hydrogen ions present and a lower degree of free-floating hydroxide molecules present. That is what OH negative means, is hydroxide, where H plus means hydrogen ions. So our bases are going to be the exact opposite. They are going to have a low concentration of free-floating hydrogen ions and a high concentration of free-floating hydroxide ions. That's why our bases are going to be represented by things like hydrogen peroxide. So any type of solution that has an oxide at the end of its name, you can safely assume this is going to be a type of base. Looking at our pH scale here, we can see that we have a pH scale which goes from as low as 0 pH, which is extremely acidic, very, very acidic, and very, very reactive. We're thinking about things like hydrochloric acid, all the way to the top end with a pH value of 14. So these are going to be our extremely, extremely basic different types of concentrations. So we're thinking about things like sodium hydroxide especially. So in the very middle, we have our neutral pH, which is going to be our pH value of 7. This is going to be more common of things like pure water. When it comes to health sciences, we're going to talk about things like stomach hydrochloric acid. That's going to be a hydrochloric acid that exists only in the stomach, extremely acidic, used for digesting our various types of proteins once they hit the stomach. And then we have our different levels of urine pH as well. Urine pH can be anywhere from this level of about 4.5 pH up to about 8 pH. And the reason for this high variance in pH for when it comes to the concentration of urine is that it depends very much on many people's types of diets, what other types of physical activities they're going to be engaged in, if they have any other sorts of underlying health conditions that may be altering their overall urine pH. But it can be found anywhere from this 4.5 to an 8 pH concentration. When it comes to things like blood pH, though, blood pH is going to be found in a very small window right here, slightly on the basic side, where we have a normal blood pH between 7.35 to 7.45. So this is a very narrow window that we really want to exist in when it comes to our overall homeostasis, and a very good reason for why is because we're trying to keep this blood pH at a level where it is very preferable for our normal metabolic processes while also being less accepting or less able to grow various types of bacterial or viral infections, which would be typical for things when we are talking about a slightly acidic concentration. This is going to be more around where our different types of bacteria and viruses want to exist. They hate existing in anywhere on this basic scale, and they also hate existing in this extremely acidic scale. Basically everything hates existing in this extremely acidic scale. I remember there was a class I took in college chemistry where I walked into lab one day and my teacher goes, well, so I had something planned for some hydrochloric acid. He had 1 mole level or 1 molar level hydrochloric acid, which is the most acidic you can get on the scale. And he goes, I opened the container and there was a bunch of mold growing in the container. So I actually took it to the CDC because I went, this mold is like superhuman. I mean, it should not exist in this 1 mole hydrochloric acid. So he goes, long story short, I have no more hydrochloric acid anymore. So we're going to do next week's lab. And I went, okay. Back on track though with talking about the regulation of pH in the body. Again, when we're talking about regulating blood pH, we have a very narrow range that we want to exist in between that 7.35 and 7.45 level. So anything below a blood pH value of 7.35 is going to end up resulting in an acidosis level here. So this is going to be rather problematic because it can result in things like lethargy, especially sluggish speech. If left untreated, it can result in coma. It's going to be very, very problematic. When it comes to our overall levels of a blood pH above 7.45, if we get above 7.45, this is going to be what results in an alkalosis state. So this is going to be more when we have more free-floating hydroxide ions than we really need, and this is going to end up resulting in different types of symptoms, especially when it comes to uncontrollable and sustained skeletal muscle contractions, things that we would call a fasciculation, which we'll get more into when we talk about our muscular unit and our nervous system unit. But when it comes to this alkalosis and acidosis levels, what we want to do when we're treating patients that are suffering from either of these types of conditions is we want to treat them with what's called a buffer. So buffers are going to be any type of material or any type of chemical which we are using to stabilize the pH of the solution or return that solution's pH to where we want it to be. So you can think of, in the real world, you can think of buffers like we use things like chlorine in our pools in order to make sure that we keep a nice solid pH and make sure that we keep our pools nice and clean. When it comes to health sciences though, we're going to be using buffers in an intravenous solution is most often going to be the situation where we're using buffers, especially when it comes to treating things like acidosis and alkalosis, because those are going to be, if left untreated, more of an emergency scenario. So we want to make sure that we're introducing these buffers quickly enough to create the desired change and mitigate any type of lasting negative effects of that acidosis or alkalosis. So when we're talking about a patient that's going to have more of an acidosis situation, they have a low blood pH, we want to introduce a buffer that has a high pH to it so that we can return that low blood pH to rise it up the scale and get it back to that 7.35 level. So we're going to use things like a bicarbonate or a salt that we see right here. Versus when we have a patient that has an alkalosis condition, their blood pH is too high, what we want to do is use a buffer that has a low pH to it, something that's going to be rather acidic, like a carbonic acid, so that we can bring that 7.7 or 7.8, whatever value it might be, down back to that 7.35 to 7.45 range. Moving on now to talk about chemical reactions. So we need to talk about chemical reactions because this is going to be a big part for how we discuss the making and breaking of different types of chemical bonds. So different key terms to keep in mind when we talk about chemical reactions are going to be the reactants, the products. The reactants are going to be the type of ingredients or the different substances that we are using to create the overall chemical reaction, and then the products are going to be what results after the chemical reaction. So when we're talking about a chemical reaction equation, you can think of the reactants are going to be the substances found on the left side of the equation, and then the products are going to be what's found on the right side of the equation. That's going to be the simplistic way to think about the two. We'll talk about more of the specifics and more of how that's going to change per scenario in a future slide here. But just to simplify everything, you can think of the reactants are going to be the ones that we are either going to be using on that left side of the equation, things that are going to be added together, and then we have our products on the right side of the equation, things usually that are going to result after being broken down. Whenever it comes to the overall metabolism term here, metabolism is going to be our term that is going to be the sum of all the chemical reactions in your body. So when we talk about metabolism, we have two different types of metabolic processes that can happen. We have anabolism and catabolism. So anabolism is going to be where we're building things into larger molecules or creating new products, versus catabolism is going to be where we are breaking things down. So you can think of catabolism is going to be most easily represented by thinking about digesting food. We're breaking down food to create energy. And then with that energy, we are going to use it to create or drive anabolic processes that build us up. Things like building new muscle tissue, building new skeletal tissue, and other sorts of things like that. Let's quickly review your knowledge right here since we just talked about that definition of metabolism. So when we're asking about this question, the sum of all chemical reactions that occur in an organism is known as, if you go back a slide, you should easily know this is metabolism. Now, getting into more of the in-depth parts of metabolism, we'll start off by talking about decomposition reactions. So decomposition reactions are going to involve the type of reactions where we're going to take a molecule and break it into our smaller fragments. So what we have going on with this equation right here is we have our molecule AB. This is going to be our reactant. This is going to undergo this decomposition reaction signified by the arrow that we see right here. And after this reaction, we are going to end up with our products, our A molecule and our B molecule. They are going to be separate in this regard here. So this is going to be pretty typical for our different types of digestion reactions when we are trying to digest food, where we are going to go about digesting, for instance, if you had a salad for lunch or things like that, we're going to have that as our reactant. That salad go through the decomposition reaction through our digestive process is going to yield our waste products, which we are going to get rid of through our excretion process, as well as energy. So this is going to be how we are able to actually take our food and create energy out of it. This is also going to happen when we're talking about taking different types of old tissues, old bone, for instance, old blood and things like that, old blood cells, and the body is going to break those things down to give us our reactants that we're going to use to create new tissues in its place. So this is going to be the type of reaction that we call a catabolic or a catabolism metabolic reaction. So we're going to usually do this by using a process that we call hydrolysis. Now the term hydrolysis is going to indicate that we are using water in our decomposition reaction. That's what hydrolysis means. Lysis is going to be our suffix that means to break down substances. Hydro is going to be our root word that means water. So that's going to be, you're going to see a lot of this when we talk about medical terminology, is that we have different types of words that will have a full meaning behind what each part of the word is. Now on the other side of the coin, when it comes to metabolic reactions, we have our synthesis reactions as well. Synthesis is simply going to be the exact opposite of decomposition. So we're going to have our smaller molecules, smaller fragments here, our A and our B molecules. These are going to be our reactants. They're going to go through this synthetic metabolic process here and create a new compound, the AB molecule that we see right here. This is going to end up being our type of reaction that's going to create new bonds, so new bonds like new ionic bonds, new covalent bonds. However, this is not going to end up being the type of reaction that we use to create new hydrogen bonds, because hydrogen bonds are easily made via the polarity to all of our water molecules. So we're not going to see hydrogen bonding as part of synthesis reactions. Instead, the role that water is going to play in our synthesis reactions is that water is actually going to be removed from the equation right here to give what's called dehydration synthesis. So think about when we talked about water and how it reacts to all of our different solutes when they enter a solvent, and we had that hydration sphere cover each section, each of the parts of our different types of solute. So when we remove water from that solute and remove the hydration sphere from each of those molecules, it's going to allow for those molecules to create that new bond. This is going to be what we call an anabolic metabolism, an anabolic metabolism reaction. So this is going to, because we're building things, we're going to need to use energy in order to go through that anabolic reaction. Our third type of metabolic reaction that can happen here is going to be our exchange reaction. So an exchange reaction is going to have components of both decomposition and synthesis reactions. What's happening here is that we're actually going to swap the parts of our reactants as it goes through the exchange reaction to create new products here. So we can see this illustrated by our graph right here. We're going to swap the B and the D molecules in these two reactants that we see right here. Once they go through that exchange reaction and reach the product's side, now we have an AD molecule and a CB molecule as a result. Thus far, we've been talking about metabolic reactions as being in a single direction, but just keep in mind here that when we're talking about metabolic reactions in the human body, in many cases, they are going to exist in what is called an equilibrium. So you'll see up top here, we've been talking about our metabolic reactions as being just a single direction. One way leads to the other. But when we have this icon that we see right here, this double arrow is going to denote that this reaction exists at equilibrium, which means that this synthesis reaction is occurring at the same rate as this decomposition reaction going in the reverse direction is occurring in a single environment in the body. And there's a very good reason for this, is because it's going to be what helps us to maintain our overall homeostatic condition. And when it comes to driving all of these different types of reactions, one of the other things to keep in mind as well is that because we're talking about the use of energy, and energy usually exists in the form of heat, keep in mind that when we are talking about using energy/heat, there are going to be some reactions that require large amounts of energy and large amounts of heat, which would normally be pretty problematic and damaging to our cells. So the body is going to have lots and lots of special proteins called enzymes that are going to end up working by reducing the overall activation energy, or the overall amount of heat required to drive that metabolic condition. So that's going to be another important concept which we're going to cover quite soon. Now diving into our organic molecules next. Keep in mind that when we're talking about organic molecules, we are talking about those that contain carbon. Many times, though, they are going to contain not just carbon, but also hydrogen and oxygen, especially when we're talking about organic molecules found in the human body. So there are going to be four basic macromolecules that are going to make up life in general. We have our carbohydrates, our proteins, our lipids, and then our nucleic acids. The Carbohydrates, proteins, and lipids are going to be the three macromolecules which we can acquire through our diet, but the body is going to have to synthesize our nucleic acids from scratch. Looking at the table here, we can end up seeing that each of our organic molecules are going to come associated with what is called a functional group. So looking at our table that we see right here, keep in mind first that R is going to represent the organic molecule that we are discussing. So it can be any organic molecule really in this situation. Just keep in mind that R is going to be the main part of this molecule, and then everything else is going to make up what is called the functional group. The functional group is going to be what helps to create the property of that organic molecule. So when we have things like an amino group that we see right here, which is going to be associated with having a nitrogen and then two hydrogens that we see right here, this type of functional group is going to be what acts as a base, accepting hydrogen ions and changing pHs of the solution. This is going to be something that we see pretty commonly associated with various types of amino acids that we use to create proteins. When we look at the carboxyl group, we can see that the functional group molecule over here is going to include a base carbon, two oxygens, and then one hydrogen over here. This is going to give it the property of acting as an acid, which is readily available to release a hydrogen ion. This is common for when we're talking about molecules that make up fatty acids, which we use to create our lipids or fats, as well as more amino acids to create more proteins. When we take a look at the hydroxyl group here, we can see that the organic molecule is simply going to be attached to an oxygen and one hydrogen molecule that we see right here. So this is going to be significant because this is going to allow us to engage in metabolic reactions easily, such as dehydration synthesis that we see right here, as well as creating new hydrogen bonds. This is going to be the type of functional group that we see associated with our carbohydrates, more fatty acids, more amino acids, as well as more alcohols. Alcohols are going to be another type of macromolecule that we can find in the diet. It's not really going to be necessary, or not quite that necessary in the diet, as opposed to something like our proteins, our fatty acids, and our carbohydrates. Moving on to our phosphate group down here though, this is going to be the type of functional group that when we attach it to an organic molecule, this type of functional group, the phosphate, which is going to have a central phosphate ion as well as 4 oxygen ions that we see right out here. Now, this is going to be the type of group which is going to store energy. So being able to break off a phosphate group from a molecule that we see right here, this is going to be what allows us to help create new energy. So that's why this is going to be the type of group that we see commonly associated with high energy compounds, such as adenosine triphosphate, which is simply going to be abbreviated as ATP. As for our carbohydrates that we see here, carbohydrates are going to exist in a structure that we typically see involving a carbon, hydrogen, and oxygen ratio where we see 1 carbon for every 2 hydrogens as well as for every 1 oxygen that we see right here. So these carbohydrates are going to include our sugars and starches, which yield as an energy source. This is going to be very important, that carbohydrates are an excellent energy source because these carbohydrates are going to include what we call glucose. Glucose being one of our polysaccharides, named such because saccharides are going to yield the base chain for which we are going to create our carbohydrates. When we use the prefix poly, this is going to end up meaning many saccharides. So we have a long chain of sugars to make up this polysaccharide carbohydrate, sugars like glucose. Glucose is going to be the only energy form for which the nervous system can actually run on. This is why it's very, very important that if you have patients who are expressing to you that they want to go on a keto diet, they say, I want to do 0 sugar, it's important that you help them with realizing that it's going to be better to do a low sugar or a low carbohydrate diet rather than a no carbohydrate diet. The body is very adept, so that if there is a decrease in the incoming availability of carbohydrates, the body will go into what is called ketosis. And in this ketosis process, the body is going to produce what are called ketone bodies that can functionally be used in place of glucose. As a result, though, it is going to be rather taxing on the nervous system. This is why the zero sugar or the true ketogenic diet is really more going to be used for patients that are having true defined neurological deficits or neurological illnesses. That's what the original ketogenic diet was designed for, is to treat those types of illnesses. But when it comes to weight loss, we really want to focus more on just a low carbohydrate diet rather than a no carbohydrate diet. So back on track though. Again, with our saccharides being the base chains that create our sugars, and poly meaning many, we know now that saccharides are going to be our, of course, base chain used to make these sugars such as sucrose, lactose, and maltose, but their structure is going to be a disaccharide. Di meaning two, which means we have two chains to make up our sucrose, lactose, and maltose molecules. When it comes to our simplest sugars, though, we're going to be referencing the monosaccharides. So the monosaccharides are simply going to have the one chain of saccharides in that cellular composition. On the topic of stacking together all of those chains to make a full molecule, we do those by taking our monomers, each one of those individual saccharides in the case of a carbohydrate, and we chain them together to create a polymer, which is going to look much like what we see right here, where we have all of these individual monomers being joined together through dehydration synthesis. So what has happened is, so if you go back to the last slide, you'll have noticed that when we're talking about carbohydrates, they are going to end up being hydrophilic, meaning that they easily dissolve in water. So because they are hydrophilic and have that hydration sphere surrounding each molecule once they enter the solution, what we need to do is we need to take the water or that hydration sphere out of the equation, dehydrate the equation here. And by doing so, now we can join these two sugar chains together, our glucose and our fructose, to create a bonded sucrose molecule. Moving on to lipids here, we can see that lipids are going to exist with a different ratio. They're mainly going to exist with a carbon to hydrogen ratio of 1 carbon for every 2 hydrogens that we see right here. Our lipids are going to end up being chains that are going to involve chains of fatty acids that can then be combined to a glycerol group right here. This glycerol molecule is going to allow us to create long chain fatty acids. So when it comes to our fatty acids, these are going to include in our typical diet things like animal fats, things like plant oils, and things like waxes. Things like, for instance, coconut oil would be an excellent example of a wax that we see right here. All of these, of course, are going to be insoluble in water. They carry those hydrophobic properties. They're going to be a very excellent source of stored energy. We actually get twice as many calories per gram of lipids as we do per gram of carbohydrates. Just to break it down here for you, for every single gram of carbohydrates that we consume, we can yield 4 total kilocalories of energy. Versus in a lipid, for every 1 gram of lipids or fats that we consume, the body can yield through the digestive process 9 kilocalories per gram of lipids. So it's an excellent source of energy. However, when it comes to the consumption of different lipids, we need to keep in mind that they are going to come, as of course, when they come in the fatty acid variety, they are going to exist in an unsaturated form or a saturated form. The saturated form that we can see right here, the fatty acid chain, is of course going to involve many, many single covalent bonds. These single covalent bonds, as a result, are going to be very easily broken. They're going to be highly reactive. However, because of this structure as a saturated fatty acid, their reactivity is going to make them rather inflammatory in the body. That's why when we typically think about things like the anti-inflammatory diet, we want to avoid these saturated fats, these animal fats, the things that we would typically think of as being solid at room temperature, like butter, for instance. This is in contrast to our unsaturated fatty acids, which, as you see, include a double covalent bond right here in the middle. The existence of this double covalent bond is more difficult to break than the single covalent variety we see in the saturated fatty acid. As a result, the unsaturated fatty acids are going to be less reactive and less inflammatory to the body, which is why our unsaturated fatty acids, those plant oils, plant-based fats, those are going to be much, much less inflammatory in the diet for our patients. As we take a look to the right of our slide right here, we'll go back to our graph that we see here. So we have, of course, when it comes to the formation of our total fatty acid chains, we're going to end up having our 3 individual fatty acid chains that we see right here. We have 2 saturated chains and 1 unsaturated chain. When we go through the dehydration synthesis reaction that we see right here, we're going to take out all of these water molecules between the fatty acid chains and the glycerol molecule. We're going to dehydrate all of those reactants and yield the products of a 3-chained fatty acid molecule known as a triglyceride, because tri is going to mean 3. Our table that we see right here is going to include more in-depth information about all of the lipids that we will find in the body. Because we're not going to be so focused on the digestive process in Anatomy and Physiology I, keep in mind that most of this information is going to be more heavily absorbed or more heavily covered in Anatomy and Physiology II. Before we move on from fatty acids, though, we need to talk about their significance to the structure of our cells, especially to the structure of our cell membrane. Because I briefly mentioned earlier in the chapter that the cell membrane is going to be composed of what's called a phospholipid bilayer. So what we mean by that is, of course, that it is going to be composed of many, many phospholipids, which are going to contain a hydrophobic fatty acid tail and a hydrophilic head. Now, this structure, having both hydrophilic and hydrophobic properties, is going to be what allows the cell membrane to be selectively permeable, a term that we're going to cover once we get into Chapter 3. But when it comes to that bilayer that I mean that we're talking about 2 phospholipids being attached to each other is going to be what makes up that entire cell membrane as it surrounds all of the organelles and all of the cytosol that we find within the cell. We're going to find a fair amount of cholesterol embedded within that cell membrane as well. This is going to be important because this is going to help determine many of the different functional properties of that cell, especially when it comes to where that cell is going to bind to. We have another test your knowledge slide that we see right here. So which type of organic molecule forms the bilayer of our cell membranes? So take a moment to think about it. That should be all you need, really. We just covered it. It's going to be our phospholipids because we have a phospholipid bilayer. It's going to be what makes up our cell membranes. As we move on to proteins here, you're going to note that these are going to be the most abundant organic molecule in the body. They're going to be made up of our amino acids as the building blocks of our proteins. Our proteins are going to be very crucial because they're going to involve Many of our different functions are going to be different types of structural proteins when it comes to our cellular morphology. There are going to be other types of proteins that serve as enzymes to help drive metabolic reactions. There are different types of proteins that are going to be crucial for the maintenance of our RNA and DNA as well. So proteins are going to be essential for our overall homeostatic regulation. When it comes to the formation of our proteins, we're going to end up having 20 different amino acids that can be used to make up all of our different proteins because we have so many available. They're going to be made up of our carbon, hydrogen, oxygen, and nitrogen ions. What we're going to end up seeing right here is we have a central carbon is going to be our base structure of our proteins, going to be flanked by our carboxyl group that we see over here, as well as our amino group that we see over here. And then our R group, of course, is going to be whatever sorts of variable type of organic molecule that we find bound to our base structure that we find right here. So when it comes to the formation of our proteins, what we're going to end up doing is having our dehydration synthesis reaction is going to end up creating those covalent bonds between the amino acids and give us what are called peptide bonds. So peptide bonds are going to be a very specific type of covalent bond unique to our proteins, especially when it comes to the formation between amino acids. Please do not mind the typo from the textbook. That is meant to say amino instead of aminon. When it comes to the structure of our proteins, they can be quite complex, especially because they are so crucial to the metabolic processes of the body. So we end up having 4 levels of structural complexity to our overall polypeptide proteins. First of all, we have our primary structure. This is just going to be when we are looking at the overall sequence of the amino acids of that protein. As far as the secondary structure goes, this is going to be where we're actually starting to look at the overall helix formation, or pleats, as they can also be found. As we see right here, the beta sheet is going to be an example of what we see as a pleat formation for our secondary structure proteins. But mainly we're going to be looking at this alpha helix shape. So this is kind of like when you take a spring and you pull it apart pretty far so that you can see the coil as it goes on its way through. This alpha helix coil shape is going to be our typical structure of how we're looking at a secondary structure protein. When we take a bigger picture look at our overall protein structure, we're going to be looking at the next level, which is our tertiary structure. So this is going to be where we see those alpha helices are going to be folded over top of each other to create a 3-dimensional shape, because what we've looked at so far with primary and secondary structure is just looking at things on a 2-dimensional aspect ratio here. But when we go to our tertiary structure, we are starting to branch out or sort of zoom out of our grand picture of the structure of our protein and beginning to look at the overall 3-dimensional shape of our protein that we see right here, giving us the example of this is going to be a smaller cut of what we call a hemoglobin protein that we see right here in our quaternary structure as we move forward. But the reason that we see a heme unit in our hemoglobin that we see right here is because heme is going to be our root word, which is going to denote iron. And this is going to be pretty obvious once we talk about the overall structure of our hemoglobin on a quaternary level, because now we're starting to see the entire shape of that protein. So the hemoglobin is going to have plenty of heme units because hemoglobin is going to be what makes up our red blood cells. It's going to be found in quite a large concentration in our red blood cells, because if you have taken a biology course or an anatomy and physiology course before, I would hope that you've already covered the concept that our red blood cells are going to carry oxygen throughout the body, and they do so by binding the oxygen molecules to the iron or the hemoglobin found on that red blood cell. So this is going to be the structure which is going to bind our oxygen molecules to be transported all throughout the rest of the body. Take another moment here to test your knowledge, looking at asking, the building blocks of proteins are, take a moment to think, are they amino acids, nucleotides, fatty acids, or monosaccharides? The answer you should be coming to is amino acids. Diving further into proteins, let's talk about enzymes. Enzymes are going to be a class of proteins that help catalyze or help accelerate chemical reactions. They do so by lowering the activation energy required for a certain metabolic reaction. We can see that played out on these graphs that we have over here on the right. So when we go through this metabolic reaction that we see in the first section, we have our reactants that require a certain level of activation energy to be introduced to the equation before we can end up creating our overall stable product that we find over here on the right hand side. Now this is a significant amount of activation energy required, or a significant amount of heat required for this typical reaction that we see right here. But we can lower that activation energy or lower the heat needed for that process by introducing this enzymatic protein that we find right here. So enzymatic proteins are also going to be pretty crucial because they are going to be reusable. They are not going to be used up, and they are not going to be permanently altered by the reaction that they participate in. So this is very crucial because we can use this enzyme to drive this lower activation again and again and again. What's also going to be pretty crucial about our enzymes is that they are going to be very specific to their type of metabolic reaction, because they are going to end up having a binding site which is going to be very specific to what's called a substrate. The substrate is going to be a molecule that we need known as a coenzyme. A typical coenzyme, or a common coenzyme that's a hot button topic in health sciences now, is going to be the magnesium ion. Magnesium is going to be a coenzyme for over 300 different metabolic reactions in the body. It's going to be very, very important. So this magnesium ion, once it reaches the enzyme, it's going to exist in a specific shape, and the binding site on the enzyme is going to reflect that very specific shape. So when that magnesium coenzyme arrives, it is only going to allow the enzyme it's intended for to drive the metabolic reaction. If it's going to come up on an enzyme that is not going to be specific to that magnesium ion, once the magnesium ion reaches that binding site, it is not going to activate that enzyme and not going to in this case, prematurely activate that metabolic process. When it comes to the different types of reactions that can be driven by this process, we are going to end up talking about our exergonic reactions and endergonic reactions. So our exergonic reactions are going to be the most common ones, and these are exergonic because they release energy. When it comes to endergonic reactions, which are less common, these are going to be the ones that actually absorb energy or absorb heat from their surrounding environment. Just like I mentioned in that previous slide here, when it comes to enzymes, they are going to exist in a very specific shape with very specific binding sites known as active sites that we see right here. So what's going to happen is we need that specific coenzyme or that specific substrate to bind to the correct site on an enzyme. Once that binding process has occurred, now we are going to be given what's called the enzyme substrate complex. The enzyme substrate complex is going to resultingly change the shape of the enzyme. And by changing the shape of the enzyme, this is going to be what signals the enzyme to actually work and actually lower the activation energy for that specific metabolic reaction. And as doing so, now we are going to be resulted with a new product. Once those substrates have left their binding sites or their active sites, the enzyme will then resume its original resting shape. This is very good because it means that we do not accidentally kick off more metabolic reactions as a result. Enzymatic reactions can be further influenced by their surrounding environment as well, especially when it comes to the surrounding environment of the temperature, pH, and salinity of the overall solution or the overall environment in which they exist. For instance, warmer temperatures are going to provide, because they provide more heat, they are going to provide more energy to help speed up different reactions. It's a big reason why, if you've ever heard of someone having a fast metabolism or such, and you go, well, they're actually running really hot. Their body actually runs at a hotter temperature. This is a big reason for why that metabolism tends to be a little bit faster, because they have more energy available to help speed up their reactions. But when it comes to the pH and salinity, however, if all of these different types of conditions are out of our normal range, it can lead to a denaturation process. Denaturation is a degradation process that occurs when different types of proteins are exposed to an unfavorable environment, and their quaternary structure begins to break down, and as a result they begin to break down and lose their overall structure. They become inert, they're not quite as useful anymore. So we want to make sure that human beings, we want to make sure that we maintain that temperature, pH, and salinity within our internal environment, and that within that homeostatic range. The other factor that can influence enzymatic reactions is how many enzymes or how many substrates are available in that reaction, which is known as the concentration of that reaction. If we have tons and tons of substrate available, but not enough enzymes available, then this reaction is actually going to end up occurring slower than if we had many of enzymes available to take in all of the extra substrate. Moving away from proteins here, let's get into talking about ATP. So ATP is going to be our abbreviation for what is known as adenosine triphosphate. So when we look at the word adenosine triphosphate down here, we need to break this word down. When we break the word down, we are going to see that adenosine means that we have an adenosine base molecule. It's going to be surrounded by tri meaning three, phosphate molecules. So this is going to be formed by combining an adenosine molecule that is going to exist as a diphosphate with an extra phosphate molecule. So the di means two, so when we add one more phosphate to the two phosphates that exist already, that's going to be what gives us our ATP with the 1, 2, 3 phosphate molecules. Now, the significance of our ADP, our adenosine diphosphate, to the ATP, adenosine triphosphate, is because when we're looking at this equilibrium metabolic reaction that we see right here, we are moving back and forth between taking our ATP molecule and breaking it down through hydrolysis and giving us our ADP plus energy. So we're taking this third molecule of phosphate and cleaving it or lysing it across that bond to release energy and give us that extra phosphate group. Versus on the other side, if we start on the left, what we're doing is taking our 2-phosphate group ADP and using energy to bind the third phosphate group. Now, this is crucial because we actually yield more energy by breaking apart that third phosphate molecule than we use to attach the third phosphate molecule here. So this is a very efficient reaction that's going to yield plenty of energy in the human body. Our final macromolecule to cover in this chapter is going to be our nucleic acids. So nucleic acids are not going to be acquired through our typical diet. They are going to instead be synthesized by the body. Our nucleic acids are going to be the base monomer that helps to make up our DNA and RNA. So we end up taking a look at the overall structure of our nucleic acids. They're going to follow the structure of carbon, hydrogen, oxygen, nitrogen, and phosphate ions. They're going to be used for the storage and transfer of genetic information. And they're going to exist in our double helix DNA molecules and our single helix RNA molecules. So you should use some I don't want to use the term shortcuts, but one of the things to keep in mind here is to just use your visual imaging to help with identifying that our DNA is going to be the double helix structure, because D in your mind should denote double nucleic acid, versus our RNA, which is going to simply be our single helix structure nucleic acid that we see here. So when it comes to our two types, DNA and RNA, we need to talk about how they're going to exist, where we end up seeing our base structure of the nucleic acid right here. They are going to be joined with what is called a nitrogenous base. So a nitrogenous base is going to exist in one of two categories. We have an adenine and a guanine are going to be what makes up our category of purines. And then we have our cytosine, thymine, and uracil are going to be what makes up our category of pyrimidines. Keep in mind here that when we talk about thymine and uracil, thymine is going to be the pyrimidine that only exists in DNA, whereas uracil is going to be the pyrimidine that only exists in RNA. The significance of our nitrogenous bases is that they are going to be what is used to create our genetic code, as we see through here. When it comes to our double-stranded nucleic acids, we are going to see our nitrogenous bases bonded via a hydrogen bond. This is very important because hydrogen bonds mean that we can cut that double-stranded nucleic acid and put it back together very easily without the use of large amounts of energy. But these nitrogenous bases, when they are bonded together with these hydrogen bonds, they are going to be done so in the form of what is called a complementary base pair. Complementary base pairs mean that we are going to bind a purine with a pyrimidine. We're never going to bind a purine with another purine or a pyrimidine with another pyrimidine. We're only going to bind them as one purine to one pyrimidine. Now, this is going to be very crucial that we do so because we want to have good genetic coding. If we have any errors to our genetic coding, we are going to end up seeing cancer, because cancer is going to rise from errors to the codons, which is going to be the sequence of 3 nitrogenous bases on our different genetic material as we see it being formed. And errors to the codons are going to be very, very problematic because it can do things like prevent the stoppage of new genetic materials. For instance, we have what's called a stop codon that tells the body when to cease making a new strand of genetic material. So if we delete that stop codon, we're just going to create more and more and more genetic information when we don't need it. So moving away from our DNA, the double-stranded nucleic acids, let's talk about RNA next. So RNA is going to be our single-stranded nucleic acid that we see right down here. RNA is going to be formed by way of splicing that DNA strand and having our enzyme travel up that DNA strand and code the new resulting nitrogenous base pairs that are going to be complementary. So that's going to be how we end up seeing the transfer between thymine in DNA being changed to uracil in RNA. Now we have 3 types of RNA. The first is going to be our messenger RNA. This is going to be the type of RNA which is made inside the nucleus of our cells using that base strand of DNA, we're going to cut that down the middle and create a resulting complementary strand of RNA material known as the messenger RNA. That is going to then travel to the ribosome. The ribosome is then going to use that mRNA, the messenger RNA, to create a new strand of RNA called the transfer RNA, which is going to match the amino acids from the original mRNA strand. Once that has done, it is going to end up helping the ribosome synthesize new proteins. This is going to be done through the use of ribosomal RNA. So ribosomal RNA is going to be what makes up the actual ribosome, and the ribosome is going to be what makes our new proteins. We have another chance to test your knowledge here, asking about what are the complementary base pairing rules for the creation of DNA. So remember that we're not going to have purines paired with other purines. So if you're looking through these answers that we see right here, you can immediately rule out our answer number 1. We're never going to have purines paired with other purines. Now, this is going to be very true when we look at the rest of our answers here. We want to make sure that we're looking for answers that are going to pair the correct purine with the correct pyrimidine. So take a moment here and think about your answer. Your answer that you should have come up with here is that adenine pairs with thymine and guanine pairs with cytosine. These are the correct complementary base pairs. You can use the mnemonic AT and GC. And finally, we have our table here comparing our DNA to our RNA strands. So we can see that we have different sorts of nitrogenous bases in the DNA versus our RNA. Our number of nucleotides included in each strand of DNA is going to be very, very much larger than the number of strands that we're going, or the number of nucleotides included in each RNA strand, as well as the shape is going to be much different. Our DNA is going to exist in our paired strands coiled in a double helix, whereas our RNA is going to be our single-stranded genetic material. It's going to exist more in a two-dimensional shape, and then of course they have much different functions. DNA being our genetic information that helps control the protein synthesis, whereas RNA is going to be what ends up carrying out the protein synthesis process. All right, so thanks for listening for Chapter 2 here. I'll be posting Chapter 3 pretty soon. Please let me know if you have any questions. Otherwise, good luck studying.